What's up, grade 11s? It is finally your time. 5 o'clock it is, and it's a Tuesday. And you know what that means. Physical sciences with Looney and TK. How are you, TK?
Good, how are you, Looney?
I'm good, thank you. What are we doing for the mindset today?
Well, today we're talking forces in equilibrium. So we're continuing talking the physics, okay, forces. We're going to look at forces in equilibrium. There shall be quite a number of areas where we would feel challenged. So get ready. You need to follow me as I explain some of these things so that you don't get confused as we move on. So it's forces in equilibrium today.
All right, mindsetters, you heard it. Forces in equilibrium is the lesson for today. So I hope you guys do enjoy it. Make sure to check us out on Facebook and Twitter at Learn Extra. Download your show notes, the videos, and the schedules on learn.mindset.co.za. I have posted the notes on our Facebook page, so make sure you go check out the Test Yourself competition details as well on our Facebook page. So all you need to do is answer the Test Yourself questions, fill in the entry form. It's on our Facebook page, all the details, everything, and then you might just stand yourself a chance to win 110 Rand Vodacom airtime. Yay! And from last night's show, Rolaizo Mutoho, you have won yourself 110 Rand airtime from Vodacom. I'm sure our peeps have contacted you, so you have your airtime. Congratulations to you. Mindsetters, if you also want to stand a chance to win, check out our Facebook page, answer the Test Yourself questions, answer everything else as well, just to, prep yourself for everything. And you might just stand yourself a chance to win that airtime. So TK.
Thank you, Looney. Now, moving on, we will be talking about forces in equilibrium. We will be explaining what that means. We'll be defining what an equilibrium is, and we will show the relationship. Now, this is critical. We'll be showing the relationship between the equilibrium and the resultant force, and of course explain something called the triangle of forces as well. Okay, now quickly, let's have a look at your challenge question here. I want you to be thinking about this as we move on. This is a challenge question that you should be working on. 3 forces in equilibrium, okay, are indicated by the triangle of forces above. Calculate the magnitude. All I want is for you to find how big these things are. F1 and F2. Go and find that out. Okay. Now, going into this equilibrium of forces, we need to know that when we have a number of forces acting on an object, these forces will be in equilibrium if their vector sum, or what we call the resultant, is equal to 0. So if there is no resultant, we have these forces acting, but there's no resultant, we say that that object is in equilibrium. The forces acting on it are in a state of equilibrium. Now, the single force that brings about balance to a number of forces acting together on an object, it's called an equilibrant. Okay? Now, there is the keyword, one of our keywords that I showed as we started. The equilibrant is a single force that brings about a balance to a number of forces acting together on an object. We call that an equilibrant. And this equilibrant is equal in magnitude to what we already know, to the resultant force. But what happens is that this equilibrant will always act in the opposite direction to the resultant force. Okay, so that's what you need to know. Quickly, just as some examples here. Let's look at these 2 forces here, F1 and F2. These 2 forces are of equal magnitude, and they act on one object. They are acting in opposite directions. In other words, as one pulls to the west, the other one is pulling to the east. So they're acting in opposite direction. Okay, if we have that situation there, like that, 200 Newton F1, 200 Newtons F2, equal in magnitude, but acting in opposite direction. Okay? The 2 forces, we say they are in equilibrium. Why? Because their resultant is 0. Okay? If you find the resultant of the two, you'll find it to be 0 because the resultant will be, the resultant force Fr will be the vector sum of the two. So it will be F1 plus F2. But because one is acting in an opposite direction to the other, we can say let the direction in the direction of F2 to be positive and this one will be negative. So you will end up saying F1 will therefore be negative 200 plus positive 200. Now, what do you get when you add those two? You definitely get a 0. So 0 resultant. So we say that these forces are in equilibrium. Okay? Now, we said that if there is a force that brings in a balance to a number of forces acting together, we call that an equilibrium. If I look at F2 without F1, we were going to have a resultant on that object there. But once I place F1 on, then I bring the object to a state of equilibrium. Therefore, it means that F1 is an equilibrium of F2. So you can say that F1 is equilibrium of F2. You can also say vice versa, that F2 is actually an equilibrium. This is not greater than, I'm just using it as a sign, all right? Some kind of sign. F2 equilibrium of F1. You can say that. So each of the two is an equilibrium to the other because it brings about balance on the other force. That's what I'm trying to say here. Now, continuing with this examples here, let's look at this situation here. This time we've got 3 forces. These forces acting on the same object. So you've got F1, you've got F3, you've got F2. They're acting on the same object, which is that object there. Okay? The 3 forces are in equilibrium if their resultant is equal to 0. So if their resultant equals to 0, in other words, when you take them tail to head, you arrange them tail to head. If you find a closed figure like this one here, the 3 forces are in equilibrium. And this force here, look at F2 and F3. F1 is the equilibrium of F3 and F2. In other words, F1 brings about balance to the 2 forces, F3 and F2. Okay, so we call that the equilibrium. Now, if the object was at rest, it will remain at rest. Nothing will happen to it because we've got 0 resultant. And again, if this object was moving, now I want you to get this very clear because some people have misconceptions about things moving and then they think, oh, once something is moving, we can't talk about forces in equilibrium. Yes, we can. Let me tell you now. If this object was moving, it would continue to move in the same direction at constant velocity if all those forces, the 3 forces, are acting on it and they are in equilibrium. They give you a closed figure when you put them tail to head. Okay, so even if something is moving, it can just continue to move with the same velocity, same speed, and in the same direction. Okay, that tells you the forces are in equilibrium. Now, when I put this statement like that, I want you to think ahead of what we're still going to do. Newton's first law of motion definitely brings this out for you clearly. The force F1 is therefore the equilibrium of F2 and F3. It is equal in magnitude to the resultant of F2 and F3, but it acts in the opposite direction. An equilibrium is therefore a single force that brings about balance or a state of equilibrium to a number of forces acting together. Okay, now, when 3 or more forces in equilibrium are arranged tail to head, you will come up with a closed figure. Okay? And when that closed figure is formed, you must know that the forces are in equilibrium. For three forces, if you have got three forces, if you arrange them tail to head, what you're going to end up with is a three-sided figure. And what do we call a three-sided figure? We call it a triangle. Okay? So a triangle will be formed. Right? Now, that triangle, in science, because we're talking forces, we give it a special name. We say it is a triangle of forces. Okay? It's a triangle of forces that will be formed. Now, when these three forces are acting together on an object, and of course being in equilibrium, their magnitude and direction can be represented successively by the three sides of a triangle. And we call this, you must note this, we call this the law of the triangle of forces. Now, this is crucial. You need to know that. You need to understand that. Okay, so this is the summary that we need to know when we're talking about forces in equilibrium. Okay, so now, remember, when we come to this triangle of forces, I want to stress that one because we're going to have a lot of it. With a triangle, there's a lot we can do. If it's a right-angled triangle, we can make use of trig ratios easily to calculate what is unknown to us. For example, we can use the cosine, the sine, the tangent, okay? Or we can also make use of the theorem of Pythagoras as well, okay? We always do that. I think you know that if we're talking a right-angled triangle. But if we don't have a right-angled triangle, what else can we do? You can make use of sine rule. You can make use of the cosine rule, okay, to calculate what is not given to you, to find out a solution to a question that has been posed to you. Okay, now let's go back to this diagram here as we draw closer to a break. When we say you are arranging these forces tail to head, quickly have a look at this here, this diagram here. You would see at the beginning, this is the force diagram that you are having. You would then have to arrange F2 and F3 in such a way that F2 begins by the head of F3, or F3 begins by the head of F2, whichever way, as long as they are tail to head. Once you do that, the tail to head from the head of the last one to the tail of the first one gives you the equilibrium. But suppose it was just for you to say, there is my F3, and there is my F2, all right? And I need to put in a resultant. So I just arrange them tail to head. The resultant will be from the tail of F3 to the head of F2. That would have been what? The resultant of the two forces. Now, when we talk equilibrium, we said an equilibrium is that single force that brings about balance to a number of forces acting together. And we said it is equal in magnitude to the resultant, but it acts in the opposite direction to the resultant. Now I want you to check something here on this. Compare this diagram to that diagram. The two diagrams actually talk about the same situation. The only thing is that here on this diagram here, you've got the direction of your force there, the third force, opposite to the direction of the force over there. Now, hence we call this one your equilibrium and that one your resultant. So you can see that the equilibrium acts in the opposite direction to your resultant force. Okay, now let me give it back to Luni.
All right, Mindset is just a few more details about the competition. Entries are open until 10 p.m. tonight, so you can enter and ask your friends to enter. remember how you answer the test yourself questions and then you fill in the entry form. Another tip from the entry form, you'll see that it asks who the presenter for today is. Just a tip, presenter equals teacher. So you'll say TK or Tracy, and yeah. And then another thing, shout outs to Daniel, Gift, Ovi, Isabel, Gracious, Tuelo, Precious, Tabo, Mukove, and Tabete. And another thing about the competition, what did I want to say? My goodness. No, I forgot. Oh yes, the winners will be the winners will be announced tomorrow. So make sure you tune into the shows with Abraham from 4 till 7, and you might just win yourself 110 Rand airtime. And with that said, we are going to take a very short break. So do stay tuned. We'll see you straight after this. Welcome back, everyone, from that break. Just a clarification for everyone. You're asking me, Luni, I can't see the test itself. It's not the actual post on the Facebook page. It's the link to your show notes. You go down, you scroll down. Tika, can you just show them the test yourself? It's on the notes, guys. If you can just...
Let me see if we have it here. There it is.
Test yourself. There's the question you need to answer. And then you fill in the entry form as well. Thank you, TK. So that's how it's done. It's the test yourself. You fill it in, you fill in the entry form, you send it through, and then you'll stand a chance to win that 110 Rand Vodacom airtime. Hope we are clear on that. So now, TK, listen, please.
Do I have all the time now?
Yes, you do.
Okay, good. Thank you. Let's come to some questions that we can work on and try to sharpen our skills and learn more from them. Okay, question number 1, okay. It says here, an object of mass 2 kilograms hangs from a cable. A man pulls the object horizontally with a force of 16 newtons. Okay, let me put the N there. I know it is here. I just want to put everything together like that. So that the cable makes an angle of 45 degrees with the vertical. Okay? So that's what we are told there. Draw a free body diagram showing all the forces acting on the object. Now, people in physics in particular, it is very helpful to try and draw or sketch what is happening there so that you understand, especially when you're not given a sketch. So I'm going to try and do that here on the side. Okay? I would say this is the point where this object is hanging. So it is hanging somewhere there. Let me say it is hanging like that. So there is the object hanging. So somebody pulls it aside. Okay? Somebody pulls it aside so that it gets to some point there. He pulls it with some force there, and I think we are told he is pulling it with a 16 Newton force. Obviously, we know there is tension in there, all right? So there is tension in that string there. And this object has got some mass, and therefore there is some gravitational force on it. So already I have drawn something that will help me understand what's happening here. That angle there, I'm told, it makes an angle of 45 degrees. So that is 45 degrees there. So I now have some sketch that is going to assist me to answer the problems or questions based on this scene or scenario that has been created for me. Now quickly, let's have a look at it. Question 1.1, I'm asked to draw a free body diagram. Now, I think in all the 3 lessons that I've given you so far, all of them had something to do with free body diagrams. People expect it. It's always there. I can't imagine a question paper in physics without this. So you may, I think, about 85% possibility that you will be asked to draw force diagrams. You will be asked to draw free body diagrams. Now let's have a look at this one here. It's a free body diagram, therefore I'm expected to represent the object by simply putting a dot, all right? Now, I can fail to show every other force, but I must at least know that there is always friction, weight. gravitational force, Fg there. And there is the force with which this man is pulling the object here. And this is 16 newtons. So just doing that, it's labeling enough. And then there is this force here, which is the tension inside that string or rope. Okay? If you want to, you can show that this thing is forming an angle with the vertical of 45 degrees. Nothing is wrong by doing that, but you don't have to. What was more important was to answer the question and show the three forces acting on that object there, so you have your force diagram. Moving on, 1.2, calculate the weight of the object. Simple, okay? Weight is the gravitational force, which is always given by the mass times gravitational acceleration. Now, what is the mass? 2 kilograms. Times, what is G? G is a constant, always at 9.8 meters per square second. And that works out to 19.6 newtons. So that is the weight of your object. Now, there is a reason why you had to find the weight. Because the next question would want you to use that weight. It says here, find the magnitude of the equilibrant. Now, the magnitude of the equilibrant, if you go back here, this is in equilibrium. It is stationary there, no movement, no resultant force acting on it. Now, if I come back to this diagram here, I can say that if I complete the parallelogram like that, which is as good as coming up with a tail-to-head method, I will find the resultant of the two forces, which is that force and this force, the weight. But what do I know about the resultant? The resultant is always equal in magnitude to the equilibrant. So I would have actually answered this question here if I find the resultant. I would have answered what is the magnitude of my equilibrant. And if you go back here, you would see here that you basically are having a 90-degree angle there. So you've got a right-angled triangle. Therefore, you can make use of the theorem of Pythagoras. So you can say that the equilibrant force would be equal in magnitude to the what? To the resultant force, which will be given by, okay, and I can actually do this here. I can square it because I'm looking at the theorem of Pythagoras. So I will say it's 16 squared plus 19.6 squared. So I can do that. Therefore, this will be equal to, okay, you work this out. Let's just use the calculator quickly. 16 squared, okay, right, 16 squared. What is happening with my calculator now? So I've got 1, 6. Oh, I need to close this thing here. So 1, 6. Oh. Right. The calculator wants to fail me again. Okay, there we go. Right. And then I have my calculator. Let's see if it works now. So 16 times 16 there. You can get your answer to be 256. All right. So this is 256 plus. Work it out again. You work out this one here. 19.6, so 19.6 times 19.6. What do you get? You get 384.16, so that's what we get, 384.16. So your equilibrant, remember now it's a square of everything that you're going to get here, will be a square of that plus, let me get that right, plus 256, all right? And then, so you're getting the square root of that, 640.25.31. Okay, so that gives you 25.31. Okay, so 25.31 newtons. This was 640.56. I think it was something like that. All right, so that's what you have. And this is your equilibrium because it must be equal to your what? To your resultant. I just use that logic thinking there that if the resultant is equal in magnitude to the equilibrium and all they want me to do is to find the magnitude, I'll just use that, because if I look at what I have here, it's a right angled triangle, so I can actually use the theorem of Pythagoras. Now, the next question on improving our skills is this one, which I like so much. Look at it. It says a free body diagram showing three forces. So we've got three forces here in equilibrium is shown below. Find, listen to the question, find the magnitude. All we want is just the magnitude of F1 by means of construction. Now, I brought this question. I know it is very difficult to work on it and show it on television screen on the smart board, but it is necessary for you to learn how to construct, to draw those constructions correctly, to find solutions to problems like this. I am told here I need to find the magnitude of F1 by means of construction. Now, where is F1? There is F1. So I need to know how big is F1. That is my question there. When I construct, so by construction, because F2 and F3 is given to me, and the angle at which they are acting to the horizontal is shown to me, let's see if I can construct it and find out what F1 is. Now, most of the things I'll be doing here will be explanations because I cannot just do it for you here on the board. Now, quickly, this is the situation that we are having. What you need to do is to complete the parallelogram. Now, let's see if we can do that. You need to complete the parallelogram. And in fact, I want to put this as number 2. Number 1 that you need to do is to come up with an appropriate scale. Now, the scale that I may use here, because I know this is 30 newtons and this is 40 newtons. An appropriate scale will be a scale that will allow you to draw this on a piece of paper. You fit it in nicely. It's not too small, it's not too big, but it's something that you can read from easily. So if I come up with a scale that says, let 1 centimeter represent 5 newtons, for example. I've got how many 5s in 30? I've got 6 of them. So I would need 6 centimeters to represent 30 newtons. So what I will do is I will draw this F1, and I think this is F1, it's F2. I'll draw F2 such that when I put my ruler down, it must give me 6 from there to there, 6 centimeters. And I must also then make use of my protractor to put that angle. In fact, what I will do first, I will put that protractor there and count 25 degrees, maybe at that point. Then I'll put down my line along that point, which is 25 degrees from the horizontal upwards, and I make it a point that 6 centimeters are shown there for 30 newtons. The down one, or that force, F, this is F2, so F3 is 40 newtons. I will put my protractor here, facing downwards like that, with a 0 line along my horizontal there, and then I will then measure. Okay, let me just erase this. I will then measure this angle here, 30 degrees. Then I put a point where that 30 degrees is. Then I put my ruler down like that, and I measure exactly 8 centimeters, because my 40 newtons will be represented by 8 newtons there, by 8 centimeters there, because I've got 8 fives in 40. Okay, so 8 there, 6 there. Once I have done that, I will then move. You see here, I think what I will do, I'll just come to this one here. All right. Because I've already, okay, let me see if I can get this one to give me a chance to, right. So let me just move it. Can I move this? All right. So what I will do, I will complete the parallelogram. This one already has moved. This one here has already moved. It's there. So I'll complete my parallelogram by taking this one and putting it down up there like that. Okay? And once I have it, that the two, by construction, they meet together at a particular point. And how would I have done that? I would have taken my compass, place it there, and measuring that size there, measuring this size here, I will then put it here and make a mark there. Okay? So I would make a mark there like that. I would make a mark there like that. Let me use a different color here. Then I would also then put my protractor from there to there and put it up there and make another mark here. Where the two meet, that's where my line is going to go. In other words, my resultant is going to be something that passes through there. And I have my resultant like that. Now, why am I getting the resultant? Because I know that the magnitude of my equilibrium will be equal to the magnitude of the resultant. So I have that resultant. Now, what is there for me to do now to answer this question fully is to take my ruler, okay, and put it down here and measure the length of this line here. Okay, so from there to there, I measure that length. If I measure it correctly, and if you measure it correctly, it will work out or gives you something like 12,5 centimeters. Okay? Now, if you have got 12,5 centimeters, yet according to your scale, now let's go back to the scale. Yet according to the scale, 1 centimeter is 5 newtons. It means that you would have 12,5 times 5 newtons for that force. And what does it work out to be? Then you come to your calculator and you can actually get that easily. Okay, let's work it out. So you have 12,5 times 5. Okay, and the answer is 62,5. So 62,5 newtons. 62,5 newtons. That is your equilibrium. Okay? So your equilibrium, the magnitude of your equilibrium, it's 62,5. Now, I cannot overemphasize the fact that with construction, there are stages that you need to follow. Let me summarize it by saying this. 1, make sure you come up with the right scale. Practice how to come up with the right scale. 2, then make your measurements, okay, according to your scale, making sure that your angle is accurate. Remember, with your protractor, getting your angles right. Then lastly, you construct You put your compass and make your lines of construction there, then you draw your line, your final line, which is your resultant. You measure the magnitude of that line, you multiply by your scale, you convert it back to the newtons, because these are not centimeters, these are newtons. We're talking about forces, and then you have your answer like that. At this point, allow me to go back to Luni.
All right. TK, Lucky, and Lalumbe say hello, and that you're the real deal.
Oh, okay.
More shout outs to Libya, Sanele, Hope, Ovi, Mukove, Ngwako, Apiwe Litabo, Itu, Miriam, Mbalentle, and Tammy. Thank you so much, Mindsetters, for tuning in. Do allow us to take a young break, but we'll see you straight after this. Welcome back, Mindsetters. I know a few of you now are like raiding me with shout outs. So, hello Andy, hello Siabong, and hello Jennifer. I hope you're happy now that I said hello to you too. So TK, challenge question time.
Thank you. Now, our challenge question here, it's something that you may not have or have done, of course, perhaps at the level of mathematics. There's a lot of mathematics that you need to apply here. But don't worry, I am going to try and take you through what you are expected to know to be able to answer it. And of course, this is what we always do as science teachers, physical sciences teachers, that when we find out that you're not as clued up in that mathematical concept, we go back to it so that you can be able to communicate in our concepts here. Because, of course, mathematics is the language of communication in science. Before we answer this question, let me quickly show you something. There is something in mathematics called the sine rule. Okay. There's something called the sine rule. Now, what does the sine rule say? The sine rule says if I want to know dimensions of a triangle and I have angles there given, and say I am given this as x and this one as z, that side. So I've got side x and side z. I've got angle theta and angle beta. The sine rule says this dimension of x divided by the sine of the angle opposite the side x, which will be, in this case, beta, would be equal to the dimension z divided by the sine of the angle opposite side z, which is theta in this case. Now, this is what the sine rule is about. And if we know that sine rule, we can use it to solve some of the problems in our science, in our physics. I know that in mathematics you may not have gotten to that level yet, but I want to introduce you to this already. Okay. Now, let's go back and see if we can apply what I have just shown you here to try and solve the problem in our challenge here, the challenge question. Look at it. It says 3 forces in equilibrium. Okay, so we have them in equilibrium. They are indicated by the triangle of forces. So we've got the triangle of forces above. Calculate the magnitude of F1 and F2. Now, if you look at this side here, the angle opposite the 200 Newton side is the 98-degree angle. Now, from the 98-degree angle, because I know that angle, I can actually find what F1 is, because F1 is a side opposite the 48-degree angle there. So I can actually use the sine rule to solve that. So quickly, I could say that, let me write here, 200 over sine 98 degrees would be equal to F1 over sine 48 degrees. Therefore, my F1, which is the force that I'm looking for, will be equal to 200 times sine 48 divided by what? Divided by sine 98 degrees. These are degrees. So I can work that out quickly. All right? Where is my calculator? So I can actually get that quite easily using my calculator. F1 is 200 sine 48. Okay? Can close that. Then I say divided by sine 98. Sine 98. Close bracket. So I get it to be 150,01. I mean, comma 09. All right, 150,09. 150,09. 150,09 newtons. That is what F1 is from here. Now the question is, how do I get F2? Look, easier as well. You just have to find that angle as well. Again, mathematics to be applied here. I just want to keep it to the sine rule. I don't want to talk about other things. So let me get what that angle is. The total angles, sum of the angles of a triangle, is equal to 180 degrees. All right? So angles of a triangle. So if I've got 98 degrees plus 48 degrees plus what I don't know, I must get 180 degrees. And what is it that I don't know? Is that x there. Okay. So you can actually work it out. That x is equal to, let's quickly get that. Let's quickly get that. So that will be 180 minus 98 minus 48. What will that angle be? This angle will be 34 degrees. Okay? So that angle there is 34 degrees. This is 34 degrees. So I can again make use of my sine rule. I would say that, I can say that, go back to what is given to me. 200 over sine 98 will be equal to F2 over sine 34. So I have that. Therefore, my F2 is equal to, all right, it's going to be 200 sine 34 divided by sine 98 degrees, of course. Okay, so I need to keep that written like that. So that will be equal to, you work that out. All right, you work that out, you'll get where the answer is. Let's work it out. So this will be equal to 200 sine 34 divided by sine 98. Okay, what do you get? 112.94. So that will be 112.94. 112.94. 112 newtons. So I have found what the forces are. F1 and F2 using the sine rule. Now, I hope you've learned something more than just science now. Let's see, perhaps you've got some questions from that you are sending to us to try and help you answer under this section on equilibrium of forces. Do we have some, Looney?
Yes, we do. From Jennifer, she's asking, can you please explain what an equilibrium is again?
Okay, let me go back to the summary. Equilibrium. What is important about the for you to know about the equilibrium is that the equilibrium is equal in magnitude to the resultant, but acts in the opposite direction. Okay, but that is not the definition of what an equilibrium is. It is just to tell you that in any situation where you've got a number of forces acting together, if you bring in that balancing force, that force will be equal to the resultant in magnitude, but it will act in the opposite direction. But basically, what is this equilibrium? An equilibrium is a single force that brings about balance to a number of forces acting together. Think of people playing tug of war, for example. And the way it is, it's like the people on my right-hand side are actually pulling everyone to their side. Now comes somebody who joins this other group on the left and pulls back, and all of a sudden, there is no more movement. No more moving to the right, no moving to the left. That person has brought in a force that is an equilibrium. In other words, it has brought about balance between the number of forces that were acting there, because each person was exerting a force there. So think of an equilibrium in that way, a single force that brings about a balance in a number of forces acting together.
All right.
Right.
And then Tammy Tusi is asking, I know when calculating the magnitude of an equilibrium using a right angle triangle, are we allowed to choose between trig ratios and Pythagoras theorem? And then he goes, refer to 1.3. If not, when do I know that I have to use trig ratios or Pythagoras?
Okay, let's go to 1.3. All right. What's the name again?
Tammy.
Tammy. Let's have a look at this. Want to come this way and try to explain it. Look, in this situation here, you are bound to use the theorem of Pythagoras because of one thing. You do have the 90-degree angle there, but you don't know the sizes of those angles there. And therefore, you can't go the route of trig ratios. Okay? But suppose you were given one of the angles. Say you were given that one. Then you could choose the angles. You can actually choose to use the trig ratios straightforward. But Tammy, to add to your question, let's have a look at that angle 45. If that angle is 45 degrees, definitely this angle here is 45 degrees as well. So basically, you can use a trig ratio to find out what that is. Okay? I just chose to use the theorem of Pythagoras because immediately I could see that one and this one, the magnitudes. But if you want to see, because 45 degrees there, it's a corresponding angle to that angle, so that angle will be 45 degrees as well. And if you realize that, you can then use a trig ratio. So, Tammy, choose what works better for you. If there's an angle there which you can see where it is, use the trig ratio. If you don't have the angle at all, you have got magnitude, sizes of the sides, use the theorem of Pythagoras. And of course, if you're having a right angled triangle.
All right, that's it. Because time.
Wow.
It's gone.
Time will never be enough for us.
All right. Thank you, TK, for the lesson. Mindsetters, thank you for tuning in. We love you, and we'll see you next week.
Bye-bye.